Okay, the purpose of this video is so that you can see how you check out your Otter, both the CPU and then also connect it to the Otter wrapper so you can download it to your board and see whether it's going to work on the hardware. And this all has to be done before you go ahead and try to program your Otter to do something. So this is all in relation to the final project. So currently on the screen, this is the memory module of the CPU. As I mentioned earlier in the class, the memory module is something that Dr. Hummel designed, and that is given to you. So if you look on Canvas, right here, this Otter memory Verilog file, or excuse me, Otter memory version 1, it's a system Verilog file. This is what you would use. Remember earlier in the quarter, from one of the assignments, you used the program. You won't need the program for this final project. The program is actually within this Otter memory, so you just need this one file. Also, here is the mem file that tests all the instructions. Okay, so that's also provided. We'll come back to this. There's a couple other things you need when we get to the wrapper part from Canvas, but to see if your CPU, your Otter CPU, simulates correctly, you need the Otter memory, because that's a piece of hardware, of course, that goes in your Otter. And then you need this test all mem file, because that's where Dr. Hummel made a listing of tests that tests every instruction to see if that your Otter CPU is working the way it should. So if we go back to Vivado and we look at this memory file here, this is where you would have to type in the test all.mem. Okay, so that's where it reads from the memory. Let's see, also before we actually look at the timing diagram of the sim, let's see, this is the test bench for the CPU, and actually you can see here it's just one test case. You know, the top of the sim file is what you would normally have, right? Your module name and logic for all the connections you're going to make between the unit under test, which is the CPU, and then whatever you call these inputs and outputs of the test bench. And then of course you need a clock, so you got the clock being created right here. And then you just have one test case. As you see here, you want to wait 60 nanoseconds, and then you just set reset to 0. We don't want to reset it. And then this input here corresponds to switch positions, and for the simulator you actually want switch 2 to be up. Now if you look at the basis board, the first switch that's furthest to the right on the basis board is switch 0. So oh, actually, take that back. For this input here, we want switch 1 to be up and all the other switches to be down. So again, if you look at your basis board, the switch furthest to the right, that's switch 0. So switch 1 is right next to it. So that's why you see this set to a hex of 2, okay, which is the same thing as a binary 2, meaning that the bit to the left of the least significant bit is 1. Okay, so switch 1 is the only switch that's up, and that corresponds to a binary 2, which is the same as a hex 2. So that's why that has 2 there. And then the bottom here is just initializing the clock to 0. So that's all you need for your test case, because you know, we just want to make sure we don't reset it. And then this input has to be equal to something, and the sim, like I said, will run if this is set to a hex 2. Then when it sims, it's just going to take that mem file and it's just going to run all the instructions in that mem file. Okay, so if your simulation runs successfully, you're going to get a timing diagram like this here? Well, I've already gone ahead and pulled some signals. Well, actually, I just had to pull just one signal from over from the scope. You know what you've been doing this quarter, where you just pull signals that are intermediate to the main inputs and outputs. You know, all these signals up here: clock, reset, interrupt. Now, interrupt was just set to 0 in the code because we're not using an interrupt, so that's why you see that's red. Well, actually, I guess it's undefined here. But you can just set it to 0, and that would get rid of that undefined. And then address here, that has the address of inputs and output devices. And then here's the write when we write to an output device. And then here's the output data. So all that's going to be already on the timing diagram when when the simulation finishes. The only internal signal that you have to add here to start is this PC out. So that's where the address of the instruction that's being executed is at. And you can see I put a divider here because for what I'm about to show you, we only need to look at these 4 signals. Okay, the PC out, this address, write, enable, and then this output data. These other 4 signals, just for what we're doing, it's not important. So the first thing you want to do to see if your Otter CPU is running this all test mem file correctly is you want to look at what the program counter is outputting for the address of instructions. Okay, so if you highlight this and then do a right click, here we go. There's this find value, okay, and then up here you can input a value, and we're going to input 22C. Okay, 22C. In that all test mem file that Dr. Hummel created, if there's a problem with your Otter CPU as it runs through that file, it will go to this address. This is like an error address indicating that something's not right. So if you come over here, or actually we can just hit the enter button on the keyboard. Okay, and it's running through. See, this is what you're hoping for. Okay, one of the things you're hoping for is that as it runs through the timing diagram, you hope that it doesn't find this value. See over here, value not found. That means that there's no errors. Okay, if there was an error, then it would go to the point in the timing diagram where that error code is. And if that happens, which it's going to happen, it happens to everyone. Okay, you're going to have at least, you're probably going to have at least several, if not, a dozen or more errors. Well, when you get a 22C, that's when you need to follow the procedure that Dr. Hummel shows in his video. Okay, and I put the video on Canvas. Okay, right here, this testing MCU, same thing as CPU, and debugging. Okay, so watch this YouTube video that Dr. Hummel made here. It shows the process that you go through when you have one of those 22C error codes. Okay, so he does a handful of examples. Okay, now the other thing you need to do, because one of the things you hope for is that you don't get a 22C like we just talked about, but that's not a 100% that you've got no problems, because it's possible that you could not have any 22C error codes, but maybe for some reason your CPU is not running through the whole test. Like maybe it's getting stuck in an infinite loop or something. Okay, so that could be another problem with the CPU that won't show up by an error code. So in addition to not having any 22C error codes. The other thing you have to check to make sure that the CPU is actually running is that it's actually going through the entire all test mem file. Okay, and the way you can do that is choose the address and do a right click. Oops. And again, choose find value. And this time what we're going to do is we're going to put in the address of the 7 segment displays, which is 1 1, then 4 zeros, and then 4 0. You might remember from some of the assignments, right, that hex 11 000040, that's the address for the 7 segment display. And what we're going to do, because you'll see this is what it looks like when we actually test it on the hardware, is that we're going to see if at this address this 7 segment display is counting up incrementally from 0 to 24 hex. Okay, it should go 0, 1, 2, 3, 4, all the way up to 24 hex. Right, and 24 hex is what in base 10? Okay, hopefully you said 36, right? Because it'd be 2 times 16, 32 plus 4, 36. So that all test mem file that Dr. Hummel created is going through 36 tests. Basically, I don't know if it exactly equates to this, but you can think of it anyway as it's testing all the real instructions, which there's about 30 some odd, right? Okay. All right, so you just come over here, we got our address in there, and we want to hit the next, and you can see that over here the cursor goes right before the address is 110040. Right here the output is all zeros, but actually the other thing we're looking for is we want to see when the write goes high, okay, this WR, because when the write goes high, that's when the data is actually being outputted to the 7 segment display. So this doesn't really mean anything since the write is not high. So let's hit next again. Okay, still write is not high. Okay, so here we hit it and you see write goes high, and at this address of the 7 segment display we got a binary 0. So that means on your hardware it would show 0, okay, which is the first test. Okay, and then we hit next again. Okay, we hit next again. There's another write high, same address, right, of the 7 segment display, and it incremented to 1. Okay, so that's good. That's what we're looking for. Okay, hit next again. Okay, we don't have a write there. Hit next again. Okay, we get another write high. Again, 7 segment display address. It's a 2. So see, it went 0, 1, 2. Okay, 3. Then 4, then 5, then 6, then 7, then 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Now it also shows a hex 25, which is 37, but I checked with Dr. Hummel and that's not actually a test. So I guess as long as it goes to 24, you should be okay. This one shows 25. You'll see that on the hardware it never shows 25. So, but anyway, if it does what you just saw there, along with you don't get an error code on the PC out of 22C, then you should be good. That means that your sim for your Otter CPU is doing what it's supposed to do. Now notice that I ran this for a period of 0.6 milliseconds, and we just went through 0 to 24 in a little under 0.3 milliseconds. What I like to do is just make sure that it goes through a second time. Like there's 0, 1, 2, 3, 4, and so on. Okay, I've already checked it, so take my word for it. It does go 0 to 24 through a second time. So that's why I made it 0.6, just so I could check it twice. You know, not run it for any longer than when I had to. Okay, so so what this means, if your CPU passes, like I said, these two parameters, right, that you don't have a 22C for PC out, and also when you look at what's being outputted to the 7-segment displays, it's counting from 0 to 24 in hex, then that means your simulation is good. So the next thing you would want to do is test this on the basis board. Okay, and that's when you need the wrapper. Okay, so here's the auto wrapper, and that is something that's given to you. Dr. Hummel designed this. Here's the auto wrapper right here. Also, when you download to the board, you'll need a constraints file, and here's the constraints file that Dr. Hummel used. Now, you'll have to most likely make some edits to both these files depending on what you called inputs and outputs. For example, here in the wrapper, this block of code right here where it says declare auto CPU, see, these are the internal signals that Dr. Hummel defined, and then these are, you know, like the CPU underscore RST, CPU underscore interrupt, and you can see he set it to 0, CPU clock, and so on. That's what he called his inputs and outputs. Now, you know, you might have called yours something different, and if you did, you'll have to edit right here to make this match what you have for your inputs and outputs in your auto CPU. Now, you won't have to edit this, but earlier in the quarter I said that you know, it's the programmer that decides the addresses for the input and output devices, and that's where it's done. It's done here in this module here, because you can see this local parameter switches. That's the address that we've been using for the switches. So, you know, you could change it to some other address, you know, if you wanted to for some reason, but I wouldn't do it for this for this class. I'm just saying, you know, at some other point, if you wanted to use this and you wanted to change the addresses for the inputs and outputs, you could. You know, here's the inputs here, and then LED 7seg. Here's the output device addresses. Let's see. I think that's all really we need to point out in the auto wrapper. Now, you would have to, you know, before you generate the bit file for the auto wrapper, you need to make this the top module. Right, so we make that the top module. And then also, I already mentioned, you know, you need a constraints file. We provide that. You can see I got my memory files here. We're using the test all. You use the test all for both the simulation and the hardware test. What did I want to look at here? Oh, the constraints file. So yeah, here's the constraints file. So you can just use this as a starting point. Again, well, I guess all of this you would just keep the same because that's what Dr. Hummel used. So actually, you shouldn't have to make any edits to this. This should be all set to go. I would just use it as is. Yeah, I don't think there's anything that relies on your code here. Doesn't look like it. Okay, I've already generated the bit file for the auto wrapper, and I downloaded it to the basis board, and I made a video. So let me show you that so you can see what it should look like on your basis board. So here we are. Let's start this. Okay, so as the LEDs are scrolling, each time an LED lights up, you know, a test is being performed. So like there's a set of tests, and then the display will increment once that set of tests is complete. So you can see it started at 0, and it's counting up in hex. Okay, it'll hit 24 and then it'll just cycle again. Okay, so just like with the sim, I like to see it cycle at least once just to make sure, but you know, if you kept this going, it would just keep going the same. It just cycles 0 to 24 over and over again. Okay, but this is what it should look like if now, you know, your CPU and your auto wrapper are all working and it's working on your board. And once you have this, then you're ready to go ahead and program it to do something. Okay, so let's see. Is there anything else I wanted to talk about? I'm just looking at my list here. Yeah, I think that was all. So, again, you know, real important is watching this video by Dr. Hummel, because he shows you the process to go through when you get a 22C error code, because you will get at least a few. You know, I think I told most people in class that, you know, I was super careful when I went through these assignments for the different hardware pieces. You know, simmed all the lower modules. Was real careful putting everything together in the top module, and I still had, I must have had probably about a dozen errors. You know, most were real silly things, just, you know, just real silly kind of stuff. But there was one major thing. Like, one major thing I had was I had trouble with my reg file because I thought I had made it so register 0 would always be 0, but because of where I had my async, you know, my assignments to give the async reads, I actually put them after the sync block, and technically it should work no matter where you put those assign statements, because they continually happen in the code, so it shouldn't matter the placement. But for some reason, I'm not sure why, I just moved those assign statements above, like I showed you in class, you know, above the always FF block, and that fixed it. So anyway, sometimes you run into stuff like that. So but yeah, Dr. Hummel, like I said, he'll show you some examples in his video, and more important than the examples, because you're bound to have different errors than what he shows. I mean, again, he shows a handful, but more important than the particular error he shows is the process, because basically wherever that 22C error is, you've got to look before, okay, that something's not right before. So you just got to kind of look at the code before the 22C error in the all test file. And one thing I should also point out is that there's a text file here of that file. Okay, so you can look at, like, I actually printed this out. I had some spare paper at my house. I mean, it's really thick, but you see, here's all the instructions that, you know, the code it's running through. And like I said, 22C is the, let's see if we can get 22C here. Yeah, when you hit 22C, somewhere it says, let's see, yep, there it is, right there. See, 22C fail. All right, so when it's a 22C, that means there was some problem. And, you know, say, well, like I said, Dr. Hummel, in his video, he does a good job showing you the process to go through, so I won't repeat what he shows. Okay, but anyway, with this information, you should now know, you know, when your Otter CPU is good, and, you know, what you have to look at in order to, you know, prove that it's good. And then in addition to that, I showed you what it looks like on the hardware when it's running that all test mem file correctly on the hardware. And again, once you have that completed, then you can go ahead and program the Otter to do something.